All right, hello everybody. Today I wanted to talk about the contamination like I had mentioned in the STAR video. So we'll look at two different kinds of contamination. We'll look at microbial contamination as well as ribosomal RNA contamination. And so the importance of these two is microbial contamination can be something, especially when we're working with multicellular organisms like mice in this case, or even humans. We can get bacterial RNA in there too. And thing for ribosomal RNA is the abundance of ribosomal RNA in cells is much, much higher than that of like mRNA. So if we were to just sequence the raw RNA from cells, we'll get a high proportion of that to be just our rRNA. So we want to detect those two levels. There's a way to here when we align the rRNA to the database, if you will, that we're going to create, we can extract the unaligned reads and then move forward with STAR in that case instead of aligning the unmapped reads from STAR. So it can go both ways. And using BWA in this case to align the rRNA or align our reads to rRNA, we can go through and use that SAMTools view and pull out those reads like we did, or like I had talked about in the last video. So BWA is one that keeps the unaligned reads, whereas STAR, you have to tell it to keep those unaligned reads in the separate file, which we had mate1 and mate2. So here on the screen is the Kraken 2 that I had mentioned. There's some release notes and everything here about, the main thing here is we want to download the database for Kraken 2. And to do that, we can go to the FTP page. See if I can find it here. Or maybe you can just go to the downloads page. And then FTP is here on top. So when we click on this link, it'll bring us here. And when we download, or if we wanted to download here, I want to download this latest one. So my window, we right click, we can copy the link location, or alternatively you can just click it and it will download, and then you can move it to whatever folder you want. But if we go to our Ubuntu window now, in here we can type wget and then paste in that link. So here we're pasting in that database link. What we can do also, or what we should do, is since we want to look at whether or not there was human contamination, since we're looking at mice, we also want to download that text file. Go back to Firefox. We want to download this text file here. And that has all of the different genomes of, or the list of genomes that are included in this database file, which we can search through to find out whether or not mouse is in there. So we don't want our reads to be mapping to mice when looking for contamination. That'll give us a false flag, but we want to make sure that human is in there. So it goes both ways. So we have both of those downloading. Let's go to the text file and see whether or not our items are in. So here's the text file. Let's see. Let's actually go to NCBI here quick. So let's look for the taxonomy for mouse and human. We want our tax ID, because in that notepad or in the text file, we can see here that we have tax IDs for these. And it's a lot easier than searching for, so tax ID is going to be unique for whatever we want. Whereas if we search for mus or mouse, we can try that here quick. MUS. So we'll get a lot of things that we potentially have to look through, right? So let's go back up to the top. Okay, and let's go CBI. So that we can hit two birds with one stone in this case. First, we'll go to taxonomy, because we want to search for taxonomy. We'll select taxonomy again. And then up here, what we want to look for is mouse. So we can type musculus. scientific name for mouse. And then we have this shows up on the right. I think alternatively, we can just type mouse, but there'll be multiple that shows up. So let's select mus musculus. And then here we'll select the main one again, because we want to include all of the mice. So mus musculus. On the right-hand side, we have our entres records, all of these. What we're interested in is going to be, nucleotide. But on this page, we also see here, we have tax ID. So we can search in our notepad, bring that back. In here, we can do find. Oh, and it's not going to show it. Let's just create a new line. So what we'll type is we can do Control F, so CTRL plus F. That brings up the the find window, right? And then once we have that, inside of our find window, we can paste something that is our tax ID. So if we move this a little bit, you can see that our tax ID on the NCBI page is 10090. So in Notepad, in here, you can do the Control F to find and then type in 10090. So I'll do that since my search doesn't show up for you. 90, and then find next. So you heard that little chime. That means that our mouse is not in our database, which is good. So if we go back to Firefox and duplicate this one, go back, type in human, or we can type in Homo sapiens too. Click on Homo sapiens, same thing. And then up here we have our tax ID as 9606. So if we go back to our notepad, and here, instead of this, we can search 9606. Let's see if it comes up with any. Okay, good. So we'll have all of our human chromosomes included in this. So then we can check whether or not there's human contamination of the mRNA reads. Great. Firefox. Let's close the human one. So like I mentioned before, we can click on the nucleotide on the right-hand side. I'll hide that row. We'll click on the subtree links, and this is just going to get us to a new page that we can later select. On the right-hand side, your mRNA probably won't be selected. It'll come up like this, and there's a lot of records. What you can do is select on rRNA. So now we have all of the ribosomal RNA for mice, and there's a few different ones, but we can send to file, and then here what we want to select, not showing the drop-down window, but FASTA. Select FASTA, and when we create file, it'll send that to be downloaded. And then what we can do is copy that to our working directory, which is going to be our home directory here with all of our files. And I copied mine over and I renamed it mouse_r capital RNA .fasta. So that's the file that gets downloaded from NCBI when you click create file. Now, what we need to do is, so right now I'm assuming that your Kraken file is downloading. Mine is already downloaded and we can see that here. But as your Kraken file is downloading, what you can go ahead and do is type in up here, well, let's get into our environment. So we'd have to do conda activate and then tutorial_environment. There we go. Now we're in our tutorial environment again, and we'll have to install conda install Kraken 2. So mine's already installed. It'll go through, start searching, but then it'll spit out requirements are already met. We'll cancel that. But so conda install Kraken 2 and then conda install BWA. And this is what we're going to use for the rRNA. That. Right now I have a job running, but I don't want that to keep popping up. Okay. Now, since we have BWA and Kraken installed, let's go back to Firefox. So BWA. So to create the index, it's really easy. We just have to type in BWA index, and then we don't need to worry about those, and we'll just put in our FASTA that we just. So back to Ubuntu, and here BWA index. So index is a program within BWA package, and then we would just type in our mouse rna.fasta. When you hit enter, it'll go through and create an index, kind of like we had done with star, but of all of the RNA files. And this will allow BWA to work faster when we get to running that. I think this actually runs really quickly too. I'm just going to delete mine, delete those, and then come back. So it's done. Pretty quick and easy. When that's done, then we can look at the script that I have running right now. It's stopped. But so we cat our accession list like we had been doing with everything else, and then use the straight up and down line and then pipe it into parallel like we've been doing. So the first program that we need to run is the aligning. We need to align all of our reads, so it's going to be our trimmed reads, to that that rRNA database that we created. So all the files that BWA just created, all we have to do is specify the FASTA file after we do the indexing, and it'll automatically find all of the indexing or indexed files because they have the same name. So we'll feed in BWA and then mem, so that's the program within BWA. We'll give it some threads with -t. -p means that we're going to feed in paired end reads. So -p says we're going to give paired end. Here, this is our database, or not our database, our index names that we have created above. And then just like we've been doing with star, we'll feed in trimmed reads, and then we'll do the brackets that have the session number that's fed in with cat. We'll do our forward and our reverse read. After that, we can pipe the results of this. So what BWA mem is going to create is a .sam file. So with star, we created the BAM file. This will create a SAM file. And instead of writing our SAM file, since it's going to be really big, we can pipe that directly into SAMtools view. So view is a sub package or a sub program of SAMtools package, and we'll write that right to a BAM file. That'll save a lot of space on our hard drive when we start running. B is going to tell SAMtools that the output we want is in BAM. So here we have BAM. And then S, just to be safe, they say that it doesn't have to be in there for the new SAMtools view, but the older versions, if you specified S, that told SAMtools view that what's being fed in is going to be a SAM file. So since the output here is .sam, so if we didn't do the rest of this line, we could just run BWA mem, and the output would be our SAM file. We're going to feed that in, tell SAMtools view that we want the output to become BAM from a SAM file, and then -O, we're specifying that output name. So we have to create that folder. That's rRNA contam. This is going to be our rRNA contamination file. And then we want the starting name of the resulting BAM file to have the same name as the input. That way we can keep track of it as we go. So assuming that is completed successfully with the and, we'll go ahead and we'll get some statistics. So flag stat, SAM tools flag stat, we'll get some statistics from that BAM file. We're going to look at all the flags within it. We'll give it -A or -at, that'll say how many cores to use. And then we'll feed the input file. So this is the same exact thing that's here in our rRNA contamination folder with the same name, and then rRNA BAM. We're going to output that to rRNA.out. So what does that look like? So we'll change directories to rRNA contam, and then here we'll do nano, and then srr 2121 770 _ rRNA.out. So this is what is output from flagstat. So we have all of our different statistics here. And the one that we're mainly focused on is going to be this. This means only about 2% of our reads are mapped from rRNA, which is good. So this is just for srr 2121 770. We'll get these for everything, and then we can run multi-QC to get a summary of all of the statistics. Go ahead and exit that. Now back up here. When we run this, we're just going to feed in one job, one at a time, but this all should run through all of our accession numbers. Go ahead and continue that. So since it stopped, we can do background and then one. Jobs, we got it running again. So the important thing with this is that we're not saving the SAM file. Get this now. We just have our BAM file and our output file. We're not going to use too much storage space to store our SAM file. We go back up. That's checking for microbial contamination, or not microbial contamination. That's checking for rRNA contamination. Now, if we look at microbial contamination, we'll look with Kraken. So let me get, yeah, we do have. So in here, we can look, we have our zipped file. If we do tar ls, we have the zipped file here. Zipped. Go ahead and do tar, and then zxvf, and then paste in file. And what that's going to do is it's going to create this. If we go inside of here, here are all the files that were downloaded for the database of the microbial. So that's what Kraken 2 is going to use to map our reads to. So if we go back up, we can start mapping. So let me that. All right. So if we just want to look at one quick, we can do Kraken 2 and then --d. Here we go. So for Kraken 2, we'll need our database. So --db, --db, and then we're going to have to feed it that folder. We don't have to feed it a specific file. We'll just tell it in this folder is all of the information that you need. Okay, and then we'll give it some threads. And then in the output, to make it easy to identify, instead of having to look at just the taxonomy ID, we can use names. So that'll print out the 9606 for humans, as well as saying Homo sapiens. Then we'll give it an output. We want that to be in our microcontamination folder. And then whatever the name. So if we're just going to run one quick, we can do srr 2121.770 and then .out for output. Then we'll make a report and we'll tell that to go in the same folder. So microcontamination with the 770 name .report. Okay. Then we have to let Kraken know that we have some paired end reads. And those paired end reads are the output that we used in star. So that'll be mate 1 and mate 2 that are unmapped. So star lined srr 2121.770 unmapped, and then mate 1, then we can copy this and tell it mate 2. Okay. So if we run this, what it's going to do is it's going to load the database into RAM, and then after it's loaded into RAM, it's going to go through and start mapping. But if we want to skip the loading into RAM part, and they recommend it for when you have a lot of samples that you're looking at, you can use memory -mapping. So that'll avoid here, that'll avoid loading the database into RAM. So instead it's going to look at the database in storage, and it should hopefully run a little bit faster. Run it right off the top, loading database information, just load some information, and then it stops the loading part. We'll instead go through and start running that in memory itself, or in the hard drive itself. Oh, that's the BWA output. So this isn't from Kraken, this is from BWA. Basically, it's saying that for 778 now, 778, that one is finished. So now it's going to go on to 779. Here is Kraken. So when looking at Kraken, this is really helpful. So if we were to spawn, like in BWA, we're only spawning one job. Here, that's not that big of a deal. But for Kraken, since it doesn't use that many cores, if we wanted to launch all 12 of ours at one time, we could do that. The only downside is without specifying memory mapping, so without telling it to not load everything into memory, it's going to try to load that database into memory 12 different times. And we don't want that. Not sure why. Taking so long. Should be way quicker. Kraken 2. All right, so now Kraken is done. Here we can see 80% of our reads that were unmapped from our, from aligning with star didn't align here either. But the Kraken database isn't entirely comprehensive. It's only 8 gigabytes. They say it's a subset, I'm pretty sure. But we can see here that 20% of the reads did map to something in that Kraken data. So if we type in microcontamination, and then in here, if we want to look at our report, we can do nano or VI srr 21.21.770.report. All right, so now we're looking at one of the output files, that report file for Kraken 2, looking at we can see here kind of those same statistics. 79% of the reads, 80% of the reads not mapped to anything using Kraken. Here we have 20% of them did map for something. If you were to scroll way down, you can see all of the different things that are mapped. But here is something really interesting. 3.5% of our reads had mapped to human. So 3.5% of the total reads were contamination from human, which is cool, but not good. Just something to keep in mind. So if we want to run that as parallel to, what we could do, and our quote, our SR numbers. Beginning, we'll type at srr, our list.text, type that into parallel, and here we can give it, let's say, for job. Okay. Here, 8 cores. Go. So now what that's going to do is it's going to go through and start mapping our contamination. That was much quicker. That took about 7 seconds. I ran it before without the memory mapping, and it took about 25 seconds or so to do each. Read in a lot. 56 million reads per minute. But so that's checking for contamination and everything. I can post all the links and stuff down below too. That way, if you guys want to go through and read some more about them, you're absolutely welcome to. But that's it for this time.